Two frozen moons harbor more water than all of Earth's oceans combined. They orbit in the cosmic deep freeze where nothing should stay liquid. Yet beneath their ice shells, vast seas have been churning for billions of years. Tonight we're discovering how these alien oceans survived in the void, and why they might contain the most important discovery in human history. Before we dive into these hidden worlds, drop a comment about what fascinates you most about space. If these cosmic mysteries intrigue you, consider subscribing. These explorations are meant to spark wonder. NASA sent a robotic explorer called Voyager 1 to Jupiter in 1979. Scientists expected Europa to look like our moon, dead, cratered, frozen solid for billions of years. The images that came back defied every prediction. Europa's surface was covered in long, straight cracks. These ridges stretched for hundreds of miles. No ancient impact craters anywhere. Something was constantly reshaping this moon's face. Scientists recognized this pattern. On Earth, ice breaks into similar lines when it floats on moving water. Europa's cracks meant one thing: liquid water was moving beneath the ice. This discovery shattered our assumptions about where oceans could exist in space. Saturn has a tiny moon called Enceladus. NASA's Cassini probe discovered something impossible there in 2005. Water was shooting into space from the moon's south pole. These aren't small drips, they're massive geysers. The water eruptions reach 500 miles high. That's higher than the International Space Station orbits Earth. Scientists found salt in the water. They found organic compounds too. This wasn't just evidence of underground water. This was the water itself, delivered directly to space for analysis. The geysers revealed something extraordinary. Enceladus was sampling its own hidden ocean for us. Scientists calculated how much water these moons actually contain. The numbers are staggering. Europa alone holds twice as much water as all of Earth's oceans combined. Earth's oceans contain about 300 million cubic miles of water. That seemed like the most water possible on any world our size. Europa's hidden ocean contains 600 million cubic miles. Enceladus adds another 25 million cubic miles to that total. These frozen moons in the outer solar system contain more liquid water than our blue planet. That reality forces us to completely reimagine where life might flourish in the universe. These moons exist where water should be instantly frozen solid. Europa sits 500 million miles from the Sun. Enceladus orbits nearly twice that distance. At those distances, sunlight provides almost no heat whatsoever. Surface temperatures plummet to minus 300 degrees Fahrenheit. That's cold enough to freeze carbon dioxide solid. Yet somehow, vast oceans remain liquid beneath the ice. Something generates enough heat inside these moons to keep their oceans from freezing. That heat source has operated continuously for billions of years. This discovery revealed that internal heat, not solar warmth, determines where liquid water can exist. The ice covering these oceans isn't thin. Europa's ice shell extends 15 miles deep. That's thick enough to bury Mount Everest twice over. Enceladus has a shell roughly 20 miles thick. These ice layers act as perfect insulation. They trap the heat generated inside the moons. They also protect the oceans from the harsh radiation of space. Without this protective barrier, these waters would have boiled away billions of years ago. The ice shells preserve these oceans like a cosmic thermos bottle. The same ice that seems to hide these oceans actually makes their existence possible. These aren't pure water oceans like we have on Earth. They contain much higher concentrations of dissolved salts. That chemistry dramatically lowers the freezing point of water. On Earth, seawater freezes at 28 degrees Fahrenheit instead of 32 degrees. These alien oceans contain magnesium sulfates, sodium chlorides, and other dissolved minerals. The salt content prevents freezing even at extremely low temperatures. Scientists estimate these oceans might remain liquid down to -40 degrees Fahrenheit. This chemical antifreeze effect extends the range where liquid water can exist. The high salt content transforms what should be ice into persistent liquid seas. The weight of miles-thick ice creates extreme pressure in these hidden oceans. Europa's ocean experiences pressure 130 times greater than Earth's surface atmosphere. Imagine the weight of a 15-mile-high column of ice pressing down. Enceladus has slightly less pressure, but still 50 times greater than we experience. This crushing environment might seem hostile to life. But on Earth, creatures thrive in high-pressure environments. Deep ocean trenches contain complex ecosystems. These alien oceans offer similar conditions. The extreme pressure changes how ice and water behave in these deep oceans. The giant planets Jupiter and Saturn don't just provide gravity to hold their moons in orbit. They actively stretch and squeeze these worlds with tidal forces. As the moons orbit, they move closer to and farther from their massive parent planets. This changing distance creates a gravitational massage that flexes the entire moon. The rock and ice inside gets compressed and stretched repeatedly. This constant flexing generates friction heat throughout the moon's interior. It's the same principle that makes your hands warm when you rub them together. Tidal heating has operated for billions of years, providing the energy to maintain these liquid oceans. Both Jupiter and Saturn generate powerful magnetic fields. When electrically conductive materials move through these fields, they create detectable magnetic signatures. Salt water conducts electricity extremely well. As these moons orbit through their parent planet's magnetic field, their salty oceans generate induced magnetic fields. Space probes can measure these subtle magnetic variations. The magnetic data provided independent confirmation that electrically conductive oceans exist beneath the ice. This technique works even when we can't see the water directly. The magnetic evidence sealed the case for these hidden ocean worlds. These alien oceans contain all three ingredients that life requires anywhere in the universe. Liquid water serves as the essential solvent for biological chemistry. Chemical energy flows through these systems via various reactions. Organic compounds, carbon-based molecules exist in both oceans. The combination of water, energy, and chemistry creates environments where life could potentially emerge and thrive. These moons offer more than just water in space. They provide complete, stable ecosystems that have persisted for billions of years. The discovery that life's requirements exist beyond Earth has revolutionized our search for biology in the cosmos. The surfaces of both moons show clear evidence of recent geological activity. Europa's cracks continue to form and reshape the landscape. Enceladus geysers actively vent material into space. Dead worlds don't change their surfaces. The constant reshaping indicates that these moons remain geologically active today. Energy flows through their systems, driving continuous change and renewal. This activity suggests that their internal ocean systems are dynamic, not stagnant. Dynamic systems provide better conditions for life to emerge and evolve. These moons aren't frozen relics from the past. They're active worlds with ongoing processes that could support living ecosystems right now. Europa's surface displays thousands of parallel ridges stretching across entire hemispheres. These aren't random cracks. They form perfectly straight lines that extend for hundreds of miles without breaking. Scientists call these features double ridges because they appear as paired elevated lines. Each ridge system rises about 1,000 feet above the surrounding ice plains. The ridges run parallel to each other with mathematical precision. These patterns mirror what happens when ocean currents flow beneath floating ice on Earth. The moving water below creates stress patterns that crack the ice above in predictable ways. Europa's ridge systems provide a direct map of the circulation patterns in its hidden ocean. Certain regions of Europa look like someone took a massive ice sheet and shattered it into countless pieces. Scientists call these areas chaos terrain, broken landscapes where normal geological rules don't apply. These zones contain ice blocks the size of small mountains, all jumbled together randomly. Some blocks sit upright. Others lie tilted at impossible angles. The spaces between them are filled with smooth, younger ice that must have been liquid when it filled the gaps. This chaos happens when the ocean below breaks completely through the ice shell. Warm water floods upward, melting and rearranging the surface into a frozen puzzle. These violent mixing zones prove that Europa's ocean actively communicates with its surface. 4 massive cracks slice across Enceladus' south pole like claw marks. Scientists nicknamed them tiger stripes because of their distinctive parallel pattern. These aren't ordinary surface features. They're active volcanic vents shooting water into space. Each tiger stripe extends roughly 80 miles long and stays unusually warm compared to the surrounding terrain. Temperatures here reach -135 degrees Fahrenheit, practically tropical for this frozen world. The cracks act like pressure relief valves for the ocean below. When internal pressure builds up, water erupts through these openings at tremendous velocity. These tiger stripes transform Enceladus from a quiet ice ball into an active geological world. The ice shells on these moons experience constant stretching and compression as they orbit their giant planets. This creates predictable fracture patterns that repeat across the surface. Scientists can calculate exactly where new cracks will form based on orbital mechanics. Europa completes one orbit around Jupiter every 3.5 Earth days. During each orbit, Jupiter's gravity pulls the Moon into a slightly different shape. This repeated stretching creates linear fractures that always form perpendicular to the direction of maximum stress. The mathematics of orbital motion determines where Europa's ice will break. The clockwork precision of these stress patterns proves that tidal forces actively reshape these worlds. The thick ice shells don't just sit there frozen solid. They flow in massive circulation patterns, with warm ice rising from below and cold ice sinking from above. This process is called convection, the same phenomenon that drives weather patterns in Earth's atmosphere. Deep ice stays warmer because it sits closer to the liquid ocean below. This warmer ice becomes less dense and slowly rises toward the surface over thousands of years. Meanwhile, the cold surface ice becomes denser and gradually sinks downward to replace the rising material. This creates vast circulation cells within the ice shell. These convection patterns explain why the surface ice stays geologically active despite being miles thick. Both Europa and Enceladus show remarkably few impact craters considering their age. Our moon accumulated thousands of craters over billions of years, but these ocean moons appear almost crater-free. The scarcity of craters indicates extremely young surface ages. Scientists estimate Europa's surface averages only 90 million years old. Enceladus shows even younger terrain in some regions, possibly just a few million years old. Space debris constantly bombards every object in the solar system. The lack of accumulated impact scars means these surfaces get completely renewed on geological timescales. The missing craters prove that these ice shells remain so active they erase their own impact history. Europa displays subtle color variations across its surface, ranging from bright white ice to darker reddish-brown streaks. These colors aren't just aesthetic. They reveal the chemical composition of different regions. The reddish areas contain sulfur compounds delivered by Jupiter's radiation. When high-energy particles from Jupiter's magnetic field strike Europa's ice, they break apart water molecules and create reactive chemicals. These chemicals interact with trace sulfur from volcanic O to create the colored deposits. Enceladus shows different chemistry, with yellowish regions indicating organic compounds mixed into the ice. This material likely comes from the ocean below during geyser eruptions. The color patterns on these moons provide a chemical map of how radiation and geology interact to modify their surfaces. The ice shells aren't uniformly cold throughout their thickness. Temperature increases dramatically with depth, creating distinct layers with different properties. Surface temperatures plummet to -300 degrees Fahrenheit in the vacuum of space. At the bottom of the ice shell, where it contacts the liquid ocean, temperatures approach 32 degrees Fahrenheit, the melting point of water ice. This temperature gradient of nearly 300 degrees occurs over just 15 to 20 miles of depth. The steep temperature change creates different types of ice crystals at different levels. These temperature layers determine how the ice flows, where it cracks, and how it responds to tidal stress. The extreme pressures and temperatures within these ice shells create forms of ice that don't exist naturally on Earth. Scientists have identified multiple cryostructures layered throughout the shells. Normal ice, called Ice 1, forms only near the surface where pressures remain low. Deeper within the shell, the crushing weight creates Ice 2 and Ice 3, denser crystal forms that pack water molecules more tightly together. At the very bottom, near the ocean interface, Ice 6 might form under the most extreme pressure conditions. Each ice type has different mechanical properties that affect how the shell behaves. These exotic ice phases create a layered structure more complex than simple frozen water. Scientists couldn't directly measure how thick these ice shells are. No drill has ever penetrated them. Instead, they used ingenious indirect methods to estimate the shell thickness. Gravity measurements provided the crucial clues. Europa's ice shell creates subtle variations in the Moon's gravitational field that orbiting spacecraft can detect. By mapping these tiny gravity changes, scientists calculated that Europa's ice averages 15 miles thick. Seismic analysis of how the ice responds to tidal stress provided additional thickness estimates. The ice shell behaves like a flexible membrane stretching over a liquid layer. These detective techniques revealed that the protective ice barriers above these oceans are much thicker than anyone initially imagined. Why do some regions of Europa pull spacecraft slightly harder than others? Orbiting probes detected unexpected variations in gravitational strength across the Moon's surface. Solid ice everywhere should create uniform gravity, but the measurements showed distinct patterns. Areas with stronger gravity contained denser material beneath the surface. Areas with weaker gravity held less dense substances. Scientists ran computer models testing different internal structures. Only one scenario matched the gravity data perfectly: a liquid water layer sandwiched between solid ice above and rock below. These gravitational fingerprints provided strong evidence that Europa harbors a subsurface ocean. Europa and Enceladus show magnetic field responses despite having no molten metal cores like Earth. This should not be possible according to standard planetary physics. The mystery deepened when scientists discovered these magnetic fields switch direction predictably. Jupiter's powerful magnetic field rotates every 11 hours as the planet spins. Each time Jupiter's magnetic field sweeps across Europa, the Moon's magnetic field flips in response. Only electrically conductive material can generate induced magnetic fields this way. Pure ice does not conduct electricity, but salt water conducts extremely well. The synchronized magnetic behavior strongly suggests that electrically conductive oceans exist beneath these ice shells. Scientists studied how these moons might vibrate when struck by asteroids. These icequakes send waves through the Moon's interior, just like earthquakes. Different materials transmit seismic waves at different speeds. Solid ice transmits vibrations quickly and clearly. Liquid water slows down seismic waves and changes their frequency. Rock conducts waves differently than either ice or water. By analyzing how seismic signals traveled through these moons, scientists mapped their internal structure. The wave patterns revealed distinct liquid layers between solid zones. These seismic signatures supported the idea that liquid water occupies the middle section of these layered worlds. Europa's ice shell bends up and down by about 100 feet during each orbit around Jupiter. This massive flexing follows the gravitational rhythm of tidal forces with mathematical precision. A completely solid moon would not flex this dramatically. The ice shell behaves like a thin membrane floating on a liquid layer. As tidal forces change, the underlying ocean sloshes back and forth, causing the ice above to rise and fall. Scientists measured these vertical movements using laser altimeters on orbiting spacecraft. The flexing patterns exactly match what computer models predict for an ice shell over liquid water. The rhythmic bending shows that Europa's ice floats on an ocean that responds to tidal forces. Enceladus shoots samples of its internal ocean directly into space through its geysers. Scientists analyzed this water vapor using mass spectrometers, instruments that identify chemical compositions with extreme precision. The geyser water contains much more than pure H2O. Dissolved salts, organic molecules, and trace gases mix throughout the expelled water. The chemical signature matches what scientists expect from a mature ocean that has interacted with rocky material for billions of years. Specific salt ratios indicate the water has dissolved minerals from the moon's rocky core. Organic compounds suggest complex chemistry occurs within the hidden sea. These direct chemical samples provide definitive proof of Enceladus's subsurface ocean and reveal its sophisticated composition. Both moons slowly lose orbital energy through tidal heating. Scientists can track the effects of that energy loss over decades. The rate of orbital change reveals how much internal heat these moons generate. Europa loses orbital energy faster than a completely solid world should. The extra energy loss occurs because tidal forces heat the liquid interior, which dissipates more energy than solid ice. Enceladus shows even more dramatic orbital evolution because its interior activity releases energy and material into space. These orbital measurements provide independent support for the idea that liquid interiors exist and actively dissipate energy. Thermal inertia measures how quickly a surface responds to temperature changes. Surface behavior changes when internal heat is involved. Both Europa and Enceladus show anomalous thermal behavior. Their surfaces stay warmer than they should based purely on solar heating. Temperature measurements reveal heat flowing from the interior toward the surface. The thermal patterns indicate that internal heat generation exceeds heat loss to space. This energy balance is most consistent with tidal heating operating within internal liquid layers. These temperature profiles support the idea that active heat sources maintain liquid water beneath the ice shells. Scientists calculated the overall density of Europa and Enceladus by measuring their gravitational effects on passing spacecraft. These density values constrain what materials can exist inside these moons. Europa's density of 3.0 grams per cubic centimeter falls between pure ice and solid rock. This intermediate density requires a layered structure with ice, liquid water, and rock in specific proportions. Computer models show that roughly 8% of Europa's volume must be liquid water to match the observed density. Enceladus has lower density, indicating more ice relative to rock, but still requires a liquid layer to explain the measurements. These density calculations provide quantitative evidence for the ice-water-rock structure that defines these ocean worlds. Europa's ice shell rotates slightly faster than the Moon's rocky interior. This differential rotation indicates that the shell moves independently from the core. Only a liquid lubricating layer could allow this decoupling. If Europa were solid throughout, the ice and rock would rotate together as a rigid body. The observed rotation difference suggests that something liquid separates the outer ice from the inner rock. The amount of rotation difference constrains the thickness and properties of the intervening ocean. Thicker oceans allow greater differential motion. These rotation measurements support the idea that Europa's ice shell floats freely on a global ocean that isolates it from the rocky core. Spectroscopy analyzes how different materials absorb and reflect specific wavelengths of light. Scientists use this technique to identify chemical compounds on the surfaces of both moons. The surface compositions contain materials that originated in subsurface oceans. Europa's surface shows hydrated salts, minerals that form when ocean water evaporates and leaves behind dissolved chemicals. The specific salt types match what forms in long-lived liquid water. Enceladus displays organic compounds in its south polar region where geysers deposit ocean material. These carbon-based molecules indicate complex chemistry within the hidden sea. These spectroscopic detections show that ocean materials regularly reach the surface, confirming the existence and activity of subsurface water bodies. Europa doesn't orbit Jupiter alone. Two other large moons, Io and Ganymede, create a cosmic dance that locks all three worlds into perfect mathematical harmony. This synchronized motion is called orbital resonance. For every one orbit Ganymede completes, Europa completes exactly 2 orbits. For every 2 orbits Europa completes, Io completes exactly 4 orbits. This precise 4:2:1 ratio means the 3 moons regularly line up in the same configuration. Each alignment pulls Europa slightly off its normal path around Jupiter. The repeated gravitational tugs from its neighboring moons prevent Europa from settling into a perfectly circular orbit. Most moons eventually develop circular orbits that minimize gravitational stress. Europa cannot achieve this stable state because of its orbital resonance with neighboring moons. Instead, Europa travels an elliptical path that constantly changes its distance from Jupiter. At closest approach, Europa sits about 416,000 miles from Jupiter. At its farthest point, the distance stretches to about 417,000 miles. This 1,000-mile difference might seem small, but it creates enormous changes in gravitational force. Jupiter's gravity follows an inverse square law. Small distance changes produce dramatic force variations. The elliptical orbit ensures that Europa experiences rhythmic gravitational squeezing that never stops. Every 3.5 days, Jupiter's gravity stretches Europa into a slightly different shape as the Moon travels its elliptical orbit. This constant reshaping occurs throughout the Moon's entire interior. The deformation works like kneading duff on a planetary scale. When Europa approaches Jupiter, stronger gravity pulls the Moon into an elongated football shape. When Europa recedes, weaker gravity allows the Moon to relax back toward a sphere. This repeated flexing creates friction within Europa's interior materials. Rock grinds against rock. Ice crystals slide past each other. The friction converts orbital motion into heat energy. The internal deformation transforms Europa into a gravitational heat engine that operates continuously. Europa's liquid ocean doesn't rotate at exactly the same speed as its outer ice shell. This creates a shearing motion between the 2 layers that generates additional heat through friction. Scientists call this phenomenon differential rotation. The ice shell responds quickly to Jupiter's gravitational forces because it's solid and rigid. The liquid ocean responds more slowly because fluid motion takes time to develop. This difference in response time means the ocean and ice shell experience different amounts of tidal stress. The liquid layer rotates slightly faster than the solid shell above it. The shearing motion between these layers converts rotational energy into thermal energy that helps maintain the ocean's liquid state. Tidal heating doesn't only affect the ice and water layers. Europa's rocky core also experiences significant deformation that contributes to the Moon's internal heat budget. The rocky center contains radioactive elements that naturally produce heat through decay. Tidal forces enhance this radioactive heating by fracturing rock and exposing fresh mineral surfaces. The repeated compression and stretching creates new pathways for heat to flow outward. Computer models show that the rocky core contributes roughly 20% of Europa's total internal heat production. This bottom-up heating helps maintain the ocean's temperature from below. The combination of tidal heating and radioactive decay creates a dual heat source that powers Europa's hidden ocean. Europa's orbital energy doesn't simply disappear. It transforms into thermal energy through a complex series of physical processes. This energy conversion follows the fundamental laws of thermodynamics. Scientists call this transformation an energy cascade. Gravitational potential energy converts to kinetic energy as Europa's orbit changes shape. Kinetic energy converts to mechanical strain as the Moon deforms. Mechanical strain converts to heat through friction and viscous dissipation. The cascade operates continuously because orbital resonance prevents Europa from achieving gravitational equilibrium. Energy flows from Jupiter's rotation through the orbital system into Europa's interior. This energy pathway explains how Europa can generate more internal heat than it receives from distant sunlight. Tidal heating strength depends dramatically on distance from the parent planet. Moons closer to their host worlds experience much more intense heating than distant ones. Europa orbits 26 times closer to Jupiter than our Moon orbits Earth. This proximity amplifies tidal forces by thousands of times compared to the Earth-Moon system. Enceladus orbits even closer to Saturn relative to its Moon system, experiencing similarly intense heating. Mathematical calculations show that tidal heating drops off rapidly with distance following an inverse relationship, double the distance. Quarter the heating effect. The close orbital positions of Europa and Enceladus place them in cosmic sweet spots where tidal heating can maintain liquid water for billions of years. Tidal heating has operated continuously since these moons formed over 4 billion years ago. The energy source shows no signs of diminishing because it draws from the rotational energy of massive planets. Jupiter and Saturn contain enormous amounts of rotational energy that decreases extremely slowly. Computer simulations indicate that tidal heating will continue for many billions of years into the future. The energy supply far exceeds the heating requirements to maintain liquid oceans. This long-term sustainability distinguishes tidal heating from other energy sources like radioactive decay, which weakens over time. The cosmic clockwork of orbital resonance provides reliable heating across geological timescales. The billion-year persistence of tidal heating makes these ocean worlds permanent features of the solar system. Tidal heating doesn't warm these oceans uniformly. The energy input varies with depth, creating distinct temperature zones that structure the liquid environment. Maximum heating occurs where deformation stress reaches its peak. In Europa's ocean, the warmest water sits near the middle depth where rock liquid, and ice interfaces create the strongest tidal stress. The ocean bottom stays cooler because the rocky core deforms less than liquid water. The ocean top remains cold because it contacts the frozen ice shell above. This creates a temperature gradient that drives circulation patterns throughout the liquid layer. These temperature variations establish convection currents that distribute heat and chemicals throughout the hidden ocean system. The amount of heat these moons generate through tidal heating closely balances the amount of heat they lose to space through radiation. This equilibrium maintains stable ocean temperatures. Scientists call this balance the thermal equilibrium state. Europa produces roughly 2 trillion watts of internal heat, about twice the power consumption of the entire United States. This energy output matches the heat loss rate through the ice shell to space. Any change in this balance would either freeze the ocean solid or melt the protective ice shell completely. The current equilibrium has persisted for billions of years. This heat balance shows that tidal heating provides the right amount of energy to maintain liquid water beneath protective ice barriers. These subsurface oceans contain dramatically different chemistry than Earth sees. Instead of familiar sodium chloride table salt, these alien waters dissolve exotic mineral combinations that create unique chemical environments. Europa's ocean contains primarily magnesium sulfate, a bitter salt compound. Earth's oceans taste salty because of sodium chloride. Europa's ocean would taste intensely bitter and metallic if you could somehow sample it. This chemical difference occurs because Europa's ocean leaches minerals directly from its rocky core. Billions of years of water-rock interaction dissolves magnesium and sulfur compounds into the liquid. The alien salt chemistry fundamentally changes how chemical reactions proceed in these distant ocean worlds. Jupiter's radiation constantly bombards Europa's ice surface with high-energy particles. This cosmic radiation acts like a giant chemistry laboratory that manufactures oxygen from water molecules. The process is called radiolysis, radiation breaking apart chemical bonds. When energetic particles strike water ice, they split H2O molecules into separate hydrogen and oxygen atoms. The lightweight hydrogen escapes to space, but heavier oxygen accumulates in the ice and eventually dissolves into the ocean below. This radiation-driven chemistry creates oxygen-rich water beneath Europa's surface. The process operates continuously as long as Jupiter's magnetic field accelerates particles toward the Moon. The radiation bombardment transforms Europa's ocean into an oxidizing environment that could support oxygen-breathing life forms. Deep beneath these oceans, liquid water directly contacts rocky cores composed of silicate minerals. This water-rock interface generates hydrogen gas through chemical reactions that have operated for billions of years. Scientists call these reactions serpentinization processes. Hot water reacts with iron-bearing minerals in the rocky cores, stripping oxygen atoms from the rock and combining them with hydrogen from water molecules. This leaves behind pure hydrogen gas that bubbles upward into the ocean. On Earth, similar reactions occur at underwater volcanic vents where primitive farms harvest energy from hydrogen gas. The same chemistry operates in these alien oceans. The continuous hydrogen production provides a fundamental energy source that could fuel biological metabolism in these hidden seas. Enceladus shows remarkably high concentrations of sulfur compounds in its geyser emissions. These chemicals don't originate from the ice. They come from complex sulfur cycling within the Moon's ocean system. Sulfur exists in multiple chemical forms that can exchange electrons with other compounds. Some sulfur compounds act as electron donors while others serve as electron acceptors. This electron exchange drives chemical reactions that release energy, the same principle that powers batteries. The sulfur cycling creates opportunities for chemosynthesis, life processes that extract energy from chemical reactions rather than sunlight. Many Earth organisms use sulfur chemistry to generate metabolic energy. The abundant sulfur compounds in Enceladus ocean provide multiple pathways for life to harvest chemical energy in the absence of solar radiation. Both ocean worlds contain dissolved carbon dioxide organic molecules. Carbon-based compounds essential for all known life forms. These chemicals provide the raw materials for biological chemistry. Organic molecules include methane, formaldehyde, and more complex carbon chains. The carbon compounds form through interactions between dissolved carbon dioxide and hydrogen gas in the presence of mineral catalysts. These reactions produce the same organic building blocks that preceded life on early Earth. Spectroscopic analysis of gaseous material confirms that complex organic synthesis occurs within Enceladus Ocean. The chemical inventory includes many compounds required for amino acid and protein formation. The presence of diverse organic molecules demonstrates that these oceans support the chemistry necessary for biological systems to develop. Ocean acidity levels, measured by pH values, determine whether chemical environments can support biological processes. These alien oceans maintain pH ranges compatible with living systems. pH measures how acidic or basic a solution is on a scale from 0 to 14. Water-rock interactions naturally buffer these oceans toward neutral pH values around 8 to 9, slightly more basic than Earth's oceans. This buffering occurs because silicate minerals neutralize acids that form through various chemical processes. The stable pH environment prevents the extreme acidity that would destroy organic compounds and cellular structures. Most Earth life requires pH values between 6 and 10 to maintain proper biochemistry. The naturally buffered ocean chemistry creates conditions where biological systems could operate without being dissolved by corrosive acids. Life requires more than just water and energy. It needs essential elements like phosphorus, nitrogen, and sulfur distributed throughout the environment. These ocean worlds appear to cycle these nutrients effectively. Phosphorus is particularly critical because it forms the backbone of D-NAN-AA and energy storage molecules. Water-rock reactions slowly dissolve phosphate minerals from the rocky cores, releasing phosphorus into the ocean water. Ocean circulation distributes these dissolved nutrients throughout the liquid environment. Similar processes cycle nitrogen and other essential elements through these systems. The combination of chemical weathering and ocean mixing ensures that life-critical elements remain available. The effective nutrient cycling creates chemical conditions similar to Earth's early oceans when life first emerged. These oceans contain multiple chemical species in different oxidation states, some that readily donate electrons and others that accept them. This redox chemistry provides energy sources for metabolic processes. Redox reactions involve the transfer of electrons between different chemical compounds. The radiation-produced oxygen serves as a powerful electron acceptor, while the rock-produced hydrogen acts as an electron donor. When these chemicals react, they release energy that biological systems could harness. This creates the same type of chemical energy gradients that power life on Earth. Many microorganisms extract energy by facilitating electron transfer between oxidized and reduced compounds. The abundant redox chemistry in these alien oceans provides multiple energy pathways that could support diverse biological communities. Simple organic compounds in these oceans can combine to form increasingly complex molecules through natural chemical processes. This molecular evolution provides pathways toward biological chemistry. Complex organic synthesis requires catalytic surfaces that bring reactive molecules together. Mineral grains suspended in the ocean water provide countless catalytic surfaces where organic reactions can occur. Clay minerals and metal sulfides particularly excel at catalyzing organic chemistry. Laboratory experiments demonstrate that similar conditions can produce amino acids, lipids, and other biological precursors from simple starting materials. The chemistry operates spontaneously without requiring living organisms. The natural organic synthesis in these ocean environments creates the molecular complexity necessary for life to emerge from non-living chemistry. The rocky cores of these moons don't just provide dissolved chemicals. Their mineral surfaces actively catalyze the chemical reactions necessary for life. These surfaces concentrate reactants and accelerate biological chemistry. Catalysis speeds up chemical reactions without being consumed in the process. Iron sulfide minerals, commonly found in planetary cores, can catalyze the formation of organic compounds from dissolved gases. These same minerals likely played crucial roles in the origin of life on Earth. The vast surface area of microscopic mineral grains suspended throughout these oceans provides enormous catalytic capacity. Each grain acts as a tiny chemical factory promoting organic synthesis. The combination of diverse mineral catalysts and abundant chemical reactants creates environments where the chemistry of life can spontaneously develop and evolve toward increasing complexity. Life requires temperatures that allow liquid water to exist without being too hot or too cold. These alien oceans maintain perfect temperature ranges that biological systems could tolerate. Most of Europa's ocean stays between 32 and 50 degrees Fahrenheit. This temperature range sits well within the comfort zone for many Earth organisms. Deep-sea creatures on our planet thrive in similar cold water conditions. The consistent temperatures result from the perfect balance between tidal heating from below and cooling from the ice shell above. This thermal equilibrium has remained stable for billions of years. The steady temperature environment provides the thermal stability that complex biological chemistry requires to develop and persist. These ocean environments have remained essentially unchanged for over 4 billion years. This extraordinary stability provides the deep time necessary for life to emerge from simple chemistry and evolve into complex forms. On Earth, life required roughly 1 billion years to develop from basic chemicals into the first living cells. The stable conditions on Europa and Enceladus have persisted 40 times longer than life needed to appear on Earth. The consistent energy input, chemical environment, and temperature ranges create perfect conditions for biological evolution. Unstable environments prevent life from developing because changing conditions constantly disrupt biological processes. These alien oceans avoid this problem completely. The multi-billion-year stability transforms these worlds into natural laboratories where life has had ample time to emerge and diversify. Life needs energy to build complex molecules, maintain cellular structures, and reproduce. These ocean worlds provide not just one but multiple energy sources that could fuel diverse biological communities. Chemical energy flows through redox reactions between dissolved compounds. Tidal heating provides thermal energy that drives circulation and chemical mixing. Radiation processing creates high-energy chemicals that organisms could metabolize. This energy diversity offers multiple pathways for life to extract power from the environment. If one energy source becomes unavailable, others remain operational. The redundant energy supply systems create robust environments where biological communities could thrive even if individual energy sources fluctuate. The thick ice shells covering these oceans serve as perfect radiation shields that protect potential life from the harsh radiation environment of outer space. This protection proves essential for biological survival. Jupiter's radiation belt would sterilize any life exposed directly to space. The 15-mile thick ice shell on Europa blocks virtually all harmful radiation from reaching the ocean below. The ice absorbs and scatters the high-energy particles before they can damage biological molecules. Without this protective barrier, the intense radiation would break apart DNA and destroy cellular structures faster than life could repair the damage. The ice shell creates a safe haven where biological processes can operate without constantly fighting radiation-induced molecular destruction. These oceans don't have uniform chemistry throughout their depth. Different layers contain different chemical concentrations that could support various types of organisms adapted to specific conditions. Each chemical zone offers unique opportunities for specialized life forms. The ocean top near the ice interface contains high concentrations of radiation-processed chemicals. The ocean bottom near the rocky core stays rich in minerals dissolved from the seafloor. The middle ocean layers blend these different chemical environments, creating gradients where organisms could exploit specific chemical resources. This chemical stratification provides multiple ecological niches that could support diverse biological communities specialized for different chemical conditions. Ocean circulation systems transport dissolved nutrients, gases, and energy throughout these hidden seas. This mixing prevents essential chemicals from becoming trapped in isolated regions. Convection currents driven by tidal heating create spanning circulation. Warm water rises from the heated ocean bottom while cooler water sinks from the top, creating vertical mixing that spans the entire ocean depth. Horizontal currents, driven by the rotation of these moons, distribute materials around the entire globe. This ensures that nutrients and energy reach every part of the ocean environment. The continuous circulation creates a well-mixed chemical environment where life could access all the materials needed for growth and reproduction. The boundaries between different materials, ice and water, water and rock, create special environments where chemical reactions concentrate and accelerate. These interfaces provide ideal locations for life to emerge. Chemical activity intensifies wherever different phases meet. The ice-water boundary concentrates dissolved gases and creates temperature gradients that drive chemical reactions. The water-rock boundary generates fresh minerals and provides catalytic surfaces. These interface zones offer the same type of concentrated chemical activity found at hydrothermal vents on Earth, where many scientists believe life first originated. The multiple interface environments provide natural laboratories where the chemistry of life could develop from simple chemical reactions into complex biological systems. The extreme pressure in these deep oceans might seem hostile to life, but many Earth organisms thrive under similar high-pressure conditions. These environments could support pressure-adapted biological communities. Pressure in Europa's ocean reaches 1,300 times greater than Earth's surface atmosphere. Deep ocean creatures on Earth routinely survive pressures exceeding 1,000 atmospheres. Their cellular chemistry actually requires high pressure to function properly. The consistent high pressure in these alien oceans provides stable conditions for pressure-adapted life forms. Unlike the variable pressure environments near planetary surfaces, deep ocean pressure remains constant. The high-pressure environment offers protection from pressure changes that could disrupt biological processes, while providing the dense chemical environment that many organisms require. These completely dark environments could support thriving ecosystems based on chemosynthesis rather than photosynthesis. Life doesn't require sunlight when abundant chemical energy is available. Earth's deep ocean trenches host complex ecosystems that never see sunlight. Bacteria at hydrothermal vents extract energy from chemical reactions involving hydrogen sulfide and other compounds. These microorganisms form the base of food webs that support diverse communities. The chemical energy available in these alien oceans exceeds what's available at Earth's hydrothermal vents. The abundant chemical resources could support even more diverse biological communities. The sunless environment eliminates the need for complex light-gathering systems, while providing abundant chemical alternatives for energy generation. Scientists have discovered Earth environments remarkably similar to these alien oceans. These terrestrial analogs demonstrate that life can thrive in conditions nearly identical to what exists on Europa and Enceladus. Antarctica's Lake Vostok sits beneath 2 miles of ice and contains liquid water that has remained isolated for millions of years. Microorganisms discovered in Lake Vostok prove that life can survive in permanently dark, cold, isolated water beneath thick ice. The chemical conditions closely match those predicted for Europa's ocean. Deep-sea hydrothermal vents provide even closer analogues, with chemosynthetic life forms thriving in high-pressure, mineral-rich water with abundant chemical energy sources. These Earth parallels eliminate any doubt that the conditions on Europa and Enceladus could support living organisms using the same biological strategies that succeed on our home planet. Europa dwarfs tiny Enceladus by an enormous margin. Europa spans 1,900 miles in diameter while Enceladus measures only 300 miles across. This size difference creates fundamentally different ocean architectures. Europa's massive interior contains 600 million cubic miles of liquid water beneath a 15-mile thick ice shell. Enceladus holds just 25 million cubic miles of water under a 20-mile ice layer. The size contrast means Europa's ocean could contain entire Earth-sized regions with completely different chemical and thermal conditions. Enceladus' smaller ocean stays more uniform throughout. Europa's vast scale creates an ocean world, while Enceladus represents a more intimate water environment, where global mixing occurs more rapidly. Europa expresses its geological activity through surface cracking and ridge formation. Enceladus channels its energy into dramatic water eruptions that blast material into space. These represent two completely different geological styles. Europa's thick ice shell contains and redirects internal forces, creating the linear crack systems that crisscross its surface. The energy stays trapped within the solid shell structure. Enceladus' thinner shell cannot contain the internal pressure. The energy breaks through in concentrated locations, creating the tiger stripe geysers that vent directly to space. The geological contrast reveals how shell thickness determines whether internal energy creates surface features or explosive eruptions. Scientists can directly analyze Enceladus' ocean chemistry by flying spacecraft through its geyser plumes. Europa's ocean remains sealed beneath miles of ice that no probe has ever penetrated. This accessibility difference transforms how we study these worlds. Enceladus literally delivers ocean samples to space where instruments can analyze them immediately. The Cassini probe collected water vapor, ice particles, and dissolved chemicals directly from the subsurface sea. Europa requires indirect detective work using gravity measurements, magnetic field analysis, and surface spectroscopy to infer ocean properties. No spacecraft has ever touched Europa's actual ocean water. The accessibility advantage makes Enceladus the primary target for understanding alien ocean chemistry, while Europa remains largely mysterious. Europa's tidal heating operates through complex orbital resonance involving 3 large moons that create predictable gravitational rhythms. Enceladus receives simpler but more intense heating directly from Saturn's gravity. The heating mechanisms produce different thermal patterns. Europa's heating distributes relatively evenly throughout its interior because the resonance system creates stable, long-term tidal stress. This produces consistent ocean temperatures across the globe. Enceladus concentrates heating in its south polar region, where orbital mechanics focus tidal forces. This creates the localized hot spot that drives the tiger stripe geysers. The heating differences explain why Europa shows global geological activity while Enceladus displays dramatic activity concentrated in one hemisphere. Europa's ocean tastes of bitter magnesium sulfate salts dissolved from its rocky core. Enceladus water contains primarily sodium chloride, the same salt that flavors Earth's oceans. These chemical differences reflect distinct evolutionary histories. Europa's larger size allows more extensive water-rock interaction that dissolves magnesium and sulfur compounds from silicate minerals. The resulting chemistry creates a harsh, metallic-tasting environment. Enceladus chemistry suggests different rock types or interaction processes that produce familiar sodium and chlorine compounds. This creates ocean chemistry much closer to Earth's seas. The chemical contrast means these two worlds offer completely different environments for potential life forms adapted to specific salt compositions. Europa maintains relatively uniform temperatures throughout its ocean system. Enceladus shows extreme temperature variations with scorching hotspots next to frozen regions. The temperature patterns reflect their different energy distribution systems. Europa's global heating creates steady temperatures averaging around 40 degrees Fahrenheit throughout most of the ocean. Regional variations stay within a narrow range. Enceladus concentrated heating produces temperatures reaching 200 degrees Fahrenheit near the Tiger Stripes, while most regions remain near freezing. This creates dramatic thermal gradients. The temperature strategies demonstrate two different approaches to maintaining liquid water: steady global heating versus intense localized heat sources. Both worlds show young surfaces, but their renewal mechanisms operate on completely different timescales. Europa renews its entire surface gradually, while Enceladus creates brand new terrain in specific locations. The surface dating reveals distinct geological processes. Europa's surface averages 90 million years old with relatively uniform age across all regions. The gradual renewal suggests steady geological processes operating globally. Enceladus shows surfaces just a few million years old near the Tiger Stripes, but much older terrain in other regions. The renewal happens rapidly, but only in active zones. The age patterns prove that Europa operates as a steady geological system, while Enceladus functions more like an intermittent volcanic world. Europa maintains a thin oxygen atmosphere created by radiation splitting water molecules on its surface. Enceladus develops a temporary water vapor atmosphere from its geyser eruptions. These atmospheres form through completely different processes. Europa's oxygen atmosphere stays relatively stable because radiation continuously produces new oxygen, while the thin atmosphere slowly escapes to space. This creates a steady-state balance. Enceladus' water vapor atmosphere fluctuates dramatically based on geyser activity. When eruptions intensify, the atmosphere thickens. When activity decreases, the atmosphere dissipates rapidly. The atmospheric contrast reflects the fundamental difference between steady radiation processing versus episodic geological activity. Europa generates much stronger induced magnetic fields than Enceladus when their parent planets' magnetic fields sweep across them. This difference reveals important details about ocean conductivity. The magnetic response strength indicates ocean salt concentration and thickness. Europa's powerful magnetic signature results from its thick, highly conductive ocean filled with dissolved salts. The large volume of salty water creates strong electrical currents when exposed to Jupiter's magnetic field. Enceladus produces weaker magnetic responses because it's smaller. Less salty ocean generates smaller electrical currents when Saturn's magnetic field passes by. The magnetic contrast provides independent confirmation that Europa harbors a much larger and more chemically complex ocean system. Europa orbits deep within Jupiter's deadly radiation belt where electronics fail rapidly. Enceladus sits in a relatively benign environment where spacecraft can operate safely for extended periods. The radiation environments create opposite exploration strategies. Europa missions must use radiation-hardened equipment and minimize exposure time to prevent instrument damage. Spacecraft can only survive brief encounters before radiation destroys their electronics. Enceladus allows extended orbital missions where spacecraft can make repeated close approaches and detailed observations. The benign radiation environment permits long-term study campaigns. The exploration contrast means Europa requires quick, targeted missions while Enceladus supports comprehensive, long-duration investigations. NASA's most ambitious mission to Europa launched in 2024 with technology that can peer through miles of ice to map the hidden ocean below. The Europa Clipper spacecraft carries instruments specifically designed to measure ice thickness and ocean characteristics. The mission will make 49 close flyby passes of Europa over several years. Each flyby brings the spacecraft within 16 miles of Europa's surface, closer than any previous mission. Advanced radar systems will probe the ice shell to reveal ice thickness variations and internal structure, and help constrain the ocean below. The radar can detect liquid water through ice barriers up to 20 miles thick. This technology will create the first detailed maps of Europa's ice shell and global ocean system. The Europa Clipper mission trams Europa from a mysterious ice ball into a much more fully characterized ocean world with depth estimates and structural details. Future missions to Enceladus could place a spacecraft in permanent orbit around the tiny moon, allowing repeated flights through its water geysers for direct ocean sampling. This approach would revolutionize our understanding of alien ocean chemistry. Current mission concepts envision dozens of geyser plume encounters over multiple years. Each passage through the water eruptions would collect fresh ocean material using advanced mass spectrometers and organic compound analyzers. The accumulated data would build a much more complete chemical profile of Enceladus, hidden sea. The orbital approach allows scientists to study how geyser chemistry changes over time and correlate eruption patterns with orbital mechanics and seasonal variations. The direct sampling strategy greatly reduces uncertainty about Enceladus ocean composition by analyzing the actual water rather than inferring chemistry from indirect measurements. Engineers are studying robotic probes that can melt through miles of ice to reach the liquid oceans below. These thermal penetrators would become the first human-made objects to directly contact alien ocean water. The probes use nuclear heating systems to melt their way downward through solid ice. The penetration process takes several years as the probe slowly descends through the ice shell, maintaining a liquid water channel behind it. Advanced communication systems relay data to surface orbiters during the descent. Once the probe reaches the ocean, it could deploy miniature submarines that explore the water environment and search for signs of biological activity. The ice-penetrating technology provides the ultimate exploration capability, direct access to these hidden ocean worlds that no remote sensing technique can match. Next-generation life detection systems combine genetic material detection technology, advanced microscopy, and chemical analysis in compact packages small enough to fit on robotic probes. These instruments could provide the strongest evidence yet for whether life exists in these alien oceans. The detection systems can identify biological signatures at the molecular level. Genetic material detection devices search for patterns that could indicate living organisms. High-resolution microscopes capture images of cellular structures too small for previous instruments to detect. Chemical analyzers distinguish between organic compounds produced by biological processes versus those formed through non-living chemistry. The combination provides multiple independent ways to test for biological activity. The life detection capabilities reduce the uncertainty inherent in previous missions that could only detect conditions suitable for life rather than life itself. Advanced spacecraft will carry complete chemistry laboratories capable of analyzing thousands of different compounds in ocean samples. These analytical suites provide the detailed chemical understanding necessary to assess habitability. Mass spectrometry systems identify individual molecules with extraordinary precision. The instruments can detect organic compounds at concentrations of parts per billion, sensitive enough to find biological traces even in heavily diluted samples. Spectroscopic analyzers determine the exact ratios of different chemical elements and isotopes that reveal how long these oceans have existed and what processes shaped their chemistry. The comprehensive chemical analysis transforms these alien oceans from mysterious environments into fully characterized chemical systems with known compositions and evolutionary histories. Future missions will deploy seismometer networks on these moons' surfaces to record ice quakes and map internal structure through seismic wave analysis. This technique reveals details about ocean depth, ice shell layering, and rocky core properties. Seismic mapping works like medical CT scans, but for entire planetary bodies. Networks of sensitive vibration detectors record how earthquake waves travel through different internal materials. The wave speeds and patterns reveal whether regions contain solid ice, liquid water, or solid rock. The technique can map ocean boundaries with precision impossible through other methods. It also detects whether multiple ocean layers exist at different depths within these complex worlds. The seismic networks provide the internal structural maps necessary to understand how these ocean systems formed and evolved over billions of years. Extended monitoring missions will track these ocean worlds over decades to document seasonal changes, geological evolution, and long-term stability. This temporal perspective reveals dynamic processes invisible in brief flyby encounters. Long-term observation requires networks of orbiting spacecraft operating continuously for 20-year periods. The extended timeline captures complete orbital cycles, seasonal variations in geological activity, and gradual changes in surface features that indicate evolving subsurface conditions. Repeated measurements of the same locations over decades reveal whether these ocean systems remain stable or undergo significant changes that could affect their habitability. The long-duration monitoring provides the temporal context necessary to understand whether these worlds offer stable environments for life or dynamic systems where conditions fluctuate dramatically. Exploring these ocean worlds requires resources and expertise that exceed any single nation's capabilities. International partnerships combine the best technology and scientific knowledge from multiple space agencies into unified exploration campaigns. Collaborative missions share costs and risks while maximizing scientific returns. NASA provides launch capabilities and advanced instruments, while European and Japanese space agencies contribute specialized technologies and scientific expertise. The combined resources enable much more ambitious missions than any single agency could accomplish. International partnerships also ensure that data and discoveries benefit the global scientific community, rather than remaining restricted to individual nations. The collaborative approach transforms ocean world exploration from national projects into humanity's shared quest to understand life's potential beyond Earth. The extreme environments around these ocean worlds require entirely new technologies that push the boundaries of spacecraft engineering. These innovations benefit not just space exploration but also terrestrial applications. Radiation-resistant electronics must survive Jupiter's intense radiation belt for years. Advanced power systems generate electricity in the dim sunlight of the outer solar system, where solar panels produce minimal energy. Nuclear power sources provide reliable electricity for extended operations. Autonomous navigation systems guide spacecraft through complex gravitational environments without real-time communication with Earth controllers located hours away by radio signal. The technological demands drive innovations in robotics, materials science, and that find applications in medicine, manufacturing, and environmental monitoring. Finding life in these alien oceans would fundamentally transform our understanding of biology, evolution, and our place in the universe. The discovery represents one of the most significant scientific breakthroughs in human history. Alien life would strongly suggest that biology can emerge under suitable conditions throughout the cosmos. The discovery would reveal whether life follows universal chemical principles, or whether alien biochemistry operates through completely different mechanisms than Earth biology. Studying alien organisms would provide insights into alternative evolutionary pathways and expand our understanding of what biological systems can achieve under different environmental conditions. The scientific impact extends beyond biology into philosophy, theology, and human self-understanding by demonstrating that life may represent a common cosmic phenomenon rather than Earth's unique achievement.